Okay. This is Mehdi Soleymani. I'm postdoctoral fellow at University of California, San Francisco, Diabetes Center. Today's presentation focuses on integrative approaches to treat type 1 diabetes, or T1D. We will delve into the latest advancements in therapeutics, drug modulation, and advanced drug delivery systems, while also discussing the FDA-approved products and clinical trials that could reshape T1D treatments. This presentation is divided into 4 sections. First one is introduction. The second one is an overview of therapeutic strategies for T1D, the current challenges in T1D treatment, emerging approaches that provide new perspectives, and the conclusion. Each section builds on the latest scientific findings and clinical advancements. Type 1 diabetes represents a substantial public health challenge with significant economic implications. According to the International Diabetes Federation, or IDF, which you see here, over 5.5 million people globally live with type 1 diabetes. The cost of managing diabetes, particularly with the reliance on insulin therapy, poses a significant burden on healthcare systems worldwide. Understanding the diabetes and its complications will very helpful to us. Between 1980 to 2021, the global diabetic population grew from 108 million people to over 537 million, with projections reaching 783 million by 2045. In T1D, autoimmunity drives beta cell destruction, typically diagnosed in children and young people. Of note, the age of onset in Iran is 10 to 15 years earlier than the Western countries, which may have implications for understanding regional genetic and environmental factors in T1D pathogenesis. Beta cells within the pancreatic islets are responsible for insulin production, a process central to blood glucose homeostasis. These cells comprises approximately 65 to 90% of islet cells, as you can see here, respond rapidly to challenges in glucose concentration. Their destruction in T1D results in loss of insulin regulation. Beta cells are positioned near blood vessels, allowing them to respond efficiently to fluctuations in glucose levels. Beta cells synthesize and secrete insulin with remarkable efficiency. These cells convert proinsulin to insulin and C-peptide, releasing these molecules equimolarly. Notably, insulin secretions follows a biphasic pattern, an initial rapid release followed by sustained secretion. The function of these cells is modulated by several key transcriptional factors, including PDX1, MAFA-A, NKX6.1, NKX2.2, PAX6, and NORD1. Dysregulation in these pathways contribute to inability to produce insulin in type 1 diabetes. Okay. In type 1 diabetes, or T, declines due to autoimmune destruction. This leads to insufficient insulin production, rendering patient dependent on exogenous insulin for glucose regulations. The major symptoms of, there are the three different, two main types of diabetes. First one, T1D or type 1 diabetes. T1D is an autoimmune disease characterized by destruction of pancreatic beta cells by some autoreactive T cells. Unlike type 2 diabetes, which is characterized by insulin resistance, T1D patients lose the ability to produce insulin entirely, necessitating lifelong insulin therapy to manage blood glucose levels. You can see here there are two different types of diabetes: type 1 diabetes, type 2 diabetes, and also there is a gestational diabetes, which is during the pregnancy. We are focusing to type 1 diabetes today. Okay. I just described this one. Type 1 diabetes is a kind of the autoimmune disorder which some effector cells attack to the insulin producing islets or beta cells and destroy them. And insufficient insulin production cause type 1 diabetes complications. In type 2 diabetes, you can see a kind of insulin resistance, which is completely different with type 1 diabetes. Okay, this flowchart of some autoantibodies, as I mentioned before, followed by progressive beta cell destruction, which leads to dysglycemia. Full-blown diabetes occurs once beta cell mass falls below a critical threshold. I mentioned in the previous slides that it's under 20% of the total beta cell mass. Research has focused on early detection and intervention during the asymptomatic phase to prevent the clinical onset of type 1 diabetes. Okay, chronic hyperglycemia associated with T1D leads to numerous complications, as you can see here. Macrovascular complications include retinopathy, nephropathy, neuropathy, while microvascular complications contribute to some other diseases like cardiovascular diseases. Effective glucose control can reduce the incidence of these complications, such as long-term complications. The hallmark symptom of T1D include polyuria or frequent urination, polydipsia or excessive thirst, weight loss, and fatigue. These symptoms arise from chronic hyperglycemia and osmotic diuresis. Without insulin treatment, ketoacidosis may develop a life-threatening condition that requires immediate medical intervention. Here is a timeline of significant developments in diabetes treatment from early insulin therapy from, 1922 to modern advances like teplizumab as an antibody, anti-CD3 antibody, and glucose-responsive insulins, and also previously Lomtidra as FDA-approved cell therapy. These ongoing clinical trials are testing various therapies from insulin pumps and artificial pancreases to immunomodulation approaches aimed at treating type 1 diabetes. You can see here different types of prominent clinical trials using different strategies. This list continues to the list of innovative clinical trials, including trials targeting beta cell encapsulation and incretin-based therapies for T1D. You can see here SGL2 inhibition methods, stem cell mobilization, beta cell encapsulation, and stem cells themselves. I'll talk about most of them today. This slide highlights the various types of insulin which is available in the market, each with different onset times, peak actions, and dosage tailored to managing blood glucose levels. You can see here, for example, rapid-acting insulin with different brand names. The time action profile is usually 4 to 20 minutes after subcutaneous injection with peak at 20 to 30 minutes. And the dose is 3 times a day, up to 15 minutes before food intake. And there are other options and different categories for insulin. Non-insulin therapies, such as immunomodulation and beta cell specific approaches, are being explored to help manage and prevent the progression of T1D. You can see here different strategies like T effector cells, which is the target of these kind of antibodies or agents, are T cells or regulatory T cells or B cells. And there are other strategies that I'm going to talk about, some of them. Various therapeutic targets, including cytokine antagonists and beta cell regeneration strategies, are being developed to better manage or prevent type 1 diabetes. This slide outlines the major therapy options for T1D. As you can see here, the most effective treatment to date remains insulin therapy, derived either through injections or orally. Other approaches include pharmacotherapy, immunotherapy, and emerging cell-based therapies, which focus on protecting insulin-producing cells from autoimmune destruction or restoring them through transplantation. Cell-based therapies for T1D are categorized into two primary strategies: protection from autoimmune or alloimmune destruction and the restoration of insulin-producing cells. Techniques include immunosuppression, like immunomodulation, and stem cell transplantation, like using embryonic stem cells or induced pluripotent stem cells or iPSCs, alongside strategies to regenerate beta cells through reprogramming or proliferation. Some approaches aim to utilize mesenchymal stem cells, regulatory T cells, and other immune cells to protect or restore the function of the stem cell, islets or beta cells. This slide introduces pancreas and islet transplantation from donors as a standard option, but highlights issues like donor shortages, surgery risks, and lifeline immunosuppression strategies. It suggests alternative cell sources, including stem cell differentiation into functional beta cells, as a potential future direction for cell-based therapies in T2 diabetes or type 2 diabetes and T1 diabetes or type 1 diabetes, with emphasis on immune modulation. Various potential sources of beta cells for replacement therapies are highlighted here in this slide. These include embryonic or induced pluripotent stem cells, adult progenitor cells, beta cell replication, genetic engineering, and xenotransplantation. Additionally, strategies for regenerating endocrine pancreas cells in vivo through neogenesis, transdifferentiation, reprogramming, or replication are explored during these years. This slide explains the process of differentiating human pluripotent stem cells into stem cell-derived islets. The differentiation is broken into several stages, as you can see here in this slide, from definitive endoderm to immature beta-like cells, and finally the stem cell-derived islets. Various growth factors and small molecules guide each step to form functional beta cells. This is the thing that we are doing here at the University of California in our lab. We differentiate the stem cells, pluripotent stem cells like iPSCs, embryonic stem cells, to stem cell-derived islets, which are really functional. Different strategies for beta cell regeneration are shown here. These are including neogenesis from pancreatic progenitors, reprogramming non-beta cells like acinar or fibroblast cells, and promoting self-renewal of existing beta cells. These approaches are using to reduce beta cell death and encourage differentiation into insulin-producing cells. Most of them are doing right now in different labs and different countries. This slide illustrates advancements in producing mature beta cells from pluripotent stem cells. Directed differentiation and the use of small molecules like, latronocolin A and TGF-beta signaling promote the formation of mature insulin-producing beta cells. These cells can potentially reverse diabetes upon transplantation. The slide discusses transdifferentiation, where non-beta cells like ductal cells, acinar cells, liver cells or intestinal cells are reprogrammed to become beta-like cells through the expression of transcription factors such as PDX1, MAFA, and NGN3. This strategy could provide an alternative method to generate insulin-producing cells from non-pancreatic sources. iPSCs derived from T1 diabetes or type 1 diabetes patients can differentiate into insulin-producing beta cells, showing promise for beta cell replacement therapies. However, immune rejection remains a challenge if these cells are reintroduced into the same patient. Recent advances in generating hypoimmune iPSC lines could overcome this obstacle, making transplantation safer and more reliable and viable. We'll talk about these hypoimmune strategies to produce induced pluripotent stem cells. This slide summarizes different strategies to prevent rejection and cell-based therapies for type 1 diabetes. Key approaches include immunosuppression, autologous approach, similar haplotypes, physical protection, genetic engineering. You can see here the mechanism of each strategy and limitations for each one. Like for immunosuppression, using drugs to suppress the immune system, but this increases risk of several infections and neoplasm, or other strategies that you can see here. This slide illustrates the role of mesenchymal stem cells, or MSCs, and their extracellular vesicles in immune modulation and tissue regeneration. Key effects include effects on some T cells. These mesenchymal stem cells reduce CD8 T cell cytotoxicity and infiltration. This disease, ranging from, I don't know, teplizumab and Tregs to alpha-cept, low-dose IL-2, and verapamil for later stages, maybe. This graph outlines the potential therapeutic windows for preserving beta cell function. This is the thing that I talked before. It's a kind of the hypoimmune strategy. This slide highlights methods for engineering cells to avoid immune rejection. It presents the genetic modifications used to generate hypoimmune cells. Here, I mentioned, I can talk about it. This strategy tested by Schreiber and colleagues to prevent NK cell activation triggered by the absence of MHC class 1 and class 2 molecules. K562 cells, which are MHC class 1 and 2 deficient, were transduced to express monomeric HLA-E or HLA-G, or one of the immune regulatory molecules like PD-L1 or CD47, all of which are known to have inhibitory receptors or NK cells. They use these different strategies, HLA-G, ILT2, interaction between HLA-G and ILT2 reduce NK cell and macrophage activation. HLA-E, NKG2A, CD94, the second graph or picture, suppresses NK cell activation through the HLA-E and NKG2A, CD94 pathway. The third one, PD-1, PD-L1, modulates immune responses by inhibiting T cell activation via the PD-1, PD-L1 pathway. And the last one, CD47, SIRP-alpha, prevents macrophage activation using the don't hit me signal through CD47 SIRP-alpha pathway. The lower panel here shows the application of these modifications in primate and rodent models, demonstrating how hypoimmune cells evade immune detection, potentially allowing for successful transplantation without the need for immune suppression. This slide discusses ongoing clinical trials investigating the safety and efficacy of ex vivo expanded human autologous polyclonal Treg adoptive immunotherapy for type 1 diabetes. Regulatory T cells are kind of the cells, the T cells, CD4 positive, FOXP3 positive cells, which are responsible for regulating or modulating the immune responses, the T cell functions or effects. There are really key players in different diseases like type 1 diabetes. Several companies are testing FOXP3 Treg cells derived from autologous peripheral blood, often modified for specific indications like T1D or multiple sclerosis or MS or kidney transplants. Successes in these trials would highlight the potential of iPSCs to generate Tregs or regulatory T cells to on a kind of scale suitable or scale up, which is suitable for clinical use, representing a promising therapeutic approach to modulate immune responses in type 1 diabetes patients. This slide explains how regulatory T cells or Tregs function as living drugs by suppressing unwanted immune responses. They achieve this goal through the secretion of inhibitory signals, regulatory, some of the regulatory cytokines, and the sequestration of IL-2. Tregs can be engineered for specificity using CAR, or chimeric antigen receptor, or TCR, T cell receptor expression. They can engineer ensuring they target specific antigens. Their stability and survival depend on different factors like FOXP3 expression and metabolic pathways. These cells hold therapeutic potential in managing autoimmune disorders such as type 1 diabetes by controlling immune system overactivity. This slide illustrates the concept of using electrogenic engineering to develop a closed-loop insulin delivery systems. Today, there are lots of insulin delivery systems, but this is a very novel one. I want to just talk about it. It describes how insulin-producing cells can be engineered to respond to electrical signals, which are triggered by glucose levels monitored by a glucose sensor. When the glucose concentration rises, electrical stimulation causes calcium influx into the engineered beta cells, leading to insulin secretion via vesicle release. This innovative approach aims to create a responsive insulin delivery system that mimics natural pancreatic function, offering a potential treatment for diabetes management. This slide demonstrates how glucose receptors. This slide. This one demonstrates how glucose. Sorry, it's in GRA, glucagon. A glucagon receptor antagonist, or GRA, can stimulate beta cell regeneration in insulin-deficient mice. The process involves both replication and transdifferentiation of cells in the islets, leading to an increased beta cell mass and restored glucose homeostasis. Benefits include decreased blood glucose levels, reduced hepatic glucose production, and beta cell regeneration. However, there are disadvantages such as maybe increased cholesterol, body weight, and alpha cell hyperplasia, as well as altered glycogen storage. This slide also possesses the question of whether this approach could have similar effects on human beta cells or not. Yeah, this is the kind of the schematic of representation of closed-loop insulin delivery system, commonly used in the management of type 1 diabetes or diabetes. The system consists of an insulin pump connected to the body via an infusion set, which delivers insulin. A continuous glucose sensor measures glucose levels in the interstitial fluid, and the data is sent to the pump algorithm, which determines the insulin dose required and adjusts the delivery according to the glucose level. This system mimics the body's natural glucose regulation, aiming for higher glycemic control. This is the other system. This slide, this kind of the schematic representation, depicts the advanced architecture of closed-loop insulin delivery systems incorporating the ARISES app. It includes a real-time data from a continuous glucose monitor and an activity band which stream the clinical platform in the cloud for data visualization, training, and evaluation. Yeah, this is based on novel technologies used for glucose monitoring and insulin injections for glucose control. Okay. This slide discusses microencapsulations systems that modify the local immune environment to reduce graft immunogenicity. One strategy integrates a UDCA, which inhibits immune activation, thereby improving encapsulated beta cell viability. Another approach involves coating islet microcapsules with CXCL12, a chemokine that attracts regulatory T cells and repels effector T cells, promoting immune isolation of the graft. These methods aim to protect transplanted beta cells from immune rejection in type 1 diabetes therapies. Here, this is the kind of the, I should show this. It's this slide presents a real-time visualization of extracellular vesicles from mesenchymal stem cells in a mouse lung. The arrows highlight the point of the mesenchymal stem cells and releasing the extracellular vesicles from the mesenchymal stem cells in immunomodulation and tissue regeneration through extracellular vesicles. This data showcase how mesenchymal stem cells contribute to the therapeutic effects by secreting EVs in vivo. Okay, I want to just show this. sorry. Yeah. You can see here the mesenchymal stem cells in these arrows. This is the other mesenchymal stem cells. Now you can see the releasing of the extracellular vesicle. Yes, released. And these are the key players in immunomodulation and regeneration in different tissues. We can use them for type 1 diabetes treatment as well. Okay. This slide highlights the main limitations of in vitro differentiation of human embryonic stem cells, or ESCs, into beta cells or beta-like cells. These differentiated cells often express insulin but lack the critical function of glucose-stimulated insulin secretion. The solution proposed is in vivo differentiation, where the presence of in vivo factors plays a crucial role in completing the maturation process of these beta cells. This slide outlines the differentiation pathways of pluripotent stem cells, including both embryonic stem cells embryonic stem cells and induced pluripotent stem cells into islet organoids. You can see here, starting from definitive endoderm, the process is guided by various signaling molecules like activin A, Win3A, retinoic acid, FGF, BMP, sonic hedgehog, and Notch. These factors drive these cells through stages like pancreatic progenitor cells and endocrine precursor cells before eventually forming functional islet organoids. This slide illustrates the major roadblocks in translating embryonic stem cell, or ESCs, and induced pluripotent stem cells from laboratory research to clinical application. Challenges include tumor formation, contamination from animal products, genetic compatibility, differentiation ability, insufficient preclinical data. Regulatory, legal, political, and ethical issues further complicate the path to clinical transplantation of embryonic stem cells. These barriers need to be addressed to advance pluripotent stem cells in medical therapies. This is important for any other kind of embryonic stem cell usage. Okay, this is the study recently published in Cell Journal. Study overview that transplantation of chemically induced pluripotent stem cell islets, or CIPSCs, was performed under the abdominal anterior rectus sheath of a type 1 diabetes patient. The procedure showed promising results, leading to the restoration of insulin secretion and improved glycemic control at the 1-year follow-up of the patient. The key points of this study are: patient history includes long-term type 1 diabetes, diagnosis and multiple transplants since 2014 to 2018. The patient received autologous CIPSC islets following chemical reprogramming of adipose-derived stem cells. Results demonstrate insulin independence and decreases in glycosylated hemoglobin, or hemoglobin A1C levels. The timeline spans preclinical pre-made models to the successful patient transplantation and follow-up. This case highlights the potential of chemically induced pluripotent stem cell-derived islets as a treatment for type 1 diabetes, with an emphasis on safety and long-term insulin independency. This is the current, I think it just published within 2 weeks. Yeah, and it's a promising data. This slide presents a comparison between embryonic stem cells, induced pluripotent stem cells, and mesenchymal stem cells in terms of advantages and disadvantages for diabetes therapies. PSCs offer high differentiation capacity, but faced with the, ethical concerns and risks like teratoma formation, iPSCs avoid ethical issues and provide accessible sources for better cell replication, yet may have, mutagenic potential or challenges in long-term viability. MSCs enhance beta cell function and have lower autoimmune and oncogenic risks, but require chronic therapy and offer temporary benefits. This slide explains various bioprocessing techniques for manufacturing pancreatic islet cells from stem cells. The methods include multiplate culture, roller bottle culture, wave back bioreactor culture, and stir suspension bioreactor culture. The stir suspension bioreactor allows for control over parameters like, agitation, dissolved oxygen, feeding, pH, and temperature. It can support different forms of cell culture, including microcarriers, aggregates, and encapsulation, which are essential for scalable production of islet cells. This slide outlines the essential components for effective stem cell-derived islet therapies for type 1 diabetes patients. These pillars include the first one, generating highly functional stem cell-derived islets, achieving high insulin secretion, correct gene expression, and minimal off-target cell types. The second issue is manufacturing at scale, producing over 1 billion cells per batch, ensuring full characterization, cryopreservation for distribution, and avoiding harmful mutations like TP53. The third one is the immune protection strategies to avoid the use of immunosuppressive drugs using encapsulation, immune-modulating biomaterials, and gene-edited hypoimmune stem cell-derived islets. Effective transplantation, as you can see here, optimizing stem cell-derived islet dose, choosing the best transplantation site, minimizing the stress and death during the process, and ensuring nutrient supply post-transplantation. These are the main and key factors of successful stem cell islet therapy for treating type 1 diabetes. This slide highlights the evolution of insulin therapies during more than 100 years, addressing past, current, and future challenges. Key areas of improvement include reducing hypoglycemia, moving toward physiological insulin profile, improving quality of life, expanding access to insulin globally. Future innovations such as smart pumps, glucose-sensitive insulins, and artificial pancreas systems aim to maybe optimize insulin delivery and enhance patient outcomes while making insulin more maybe affordable and accessible. The ultimate goal is achieving more natural insulin regulation, reducing complications, and improving the cost and ease of use for each single patient. This slide outlines the essential attributes needed for functional stem cell-derived islets in diabetes therapy. The first thing is the function. Stem cell-derived islets should secrete insulin in response to glucose and the other kind of factors, but the overall insulin secretion is often lower than primary human islets. They tend to show strong first phase insulin secretion, but weaker second phase secretion. This is the other issue. Stem cell-derived islets should normalize blood glucose in diabetic mice and improve glycemic control in human and non-human primates. The second one is the chromatin accessibility. Stem cell-derived islets should maintain an open chromatin state for core endocrine genes. Challenges include, closed chromatin at multiple maturation genes and small differences in cell identity based on chromatin accessibility. The third one is the gene expression. Stem cell-derived islets needs to express core pancreatic transcriptional factors like PDX1, insulin, or CHGA. Some beta cell maturation markers like MAFA are poorly expressed in vitro. This is the other challenge. And the fourth issue is composition. Stem cell-derived islets contain pancreatic beta, pancreatic alpha, and delta cells, but off-target cell types are present as well, such as enterochromaffin cells. It's difficult to control the abundance of non-beta cell types, which might affect islet function after transplantation. This slide represents key expectation for successful treatment of diabetes. The first one, cure of hyperglycemia, restoration of normal blood glucose levels. The second one is response to glucose tolerance test, or GTT. Treated cells should show proper glucose response. The third one, evidence of approaches C-peptide secretion. This indicates insulin secretion by the treated cells. The fourth one is presence of insulin storage granules in treated cells. Treated cells should contain insulin. The fifth one is weight gain, return to normal metabolic function, evidenced by weight gain. Weight loss, and as you can remember, weight loss was one of the hallmarks of the sign of diabetes. Here, weight gain is one of the options that you can expect after treatment. Prompt return of diabetes when transfecting gene cells are removed ensures functionality of treated cells. The seventh option is the no islet regeneration in pancreatomized or streptozotocin treated animals. The control measures to confirm the treatment's effectiveness. So these benchmarks are used to assess the efficacy of regenerative diabetes therapies. Okay, this slide summarizes the complex progression and treatment approaches for type 1 diabetes. Predisposing factors like genetic, rapid growth and obesity in childhood contribute to type 1 diabetes development. Unhealthy beta cells, the beta cells suffer from inflammation, stress and metabolic challenges leading to low insulin secretion and autoantigen presentation. Beta cell destruction, type 1 diabetes involves immune-mediated destruction of beta cells. Dysfunctional immune system, an imbalance between the autoreactive T cells and regulatory T cells worsens the disease. Metabolic dearrangements, hyperglycemia, insulin resistance, and obesity emerge. And other complications, long-term complications like neuropathy, retinopathy, nephropathy, and cardiovascular disease occur. There are several different strategies. I mentioned them. I talked about them: immunomodulation, stress relief, systemic approaches such as GLP-1, RAs, and cytokine blockers are explored. Future outlook, curative treatments like stem cell therapy may be on the horizon to replace lost beta cells. This slide highlights both the challenges and potential strategies for managing T1D progression. This slide illustrates potential future therapies and technologies that could impact the treatment of individual with type 1 diabetes or T1D. The first one is artificial intelligence, which is really important these days, integration of AI to optimize diabetes management and personalized treatment plans. Second option is gene therapy, future potential for altering genes to correct underlying causes of type 1 diabetes. The third option, medical nutrition therapy, dietary intervention to help manage diabetes and metabolic health. Fourth option is drugs in the pipeline, new therapies being developed, including ladarixin or LY3502970 and SCO094. Stem cell therapy using stem cell to regenerate or replace damaged beta cells, nanotechnology, nanoparticles, and nanodevices that may offer new ways to deliver treatments. Recently introduced drugs and also statin therapy. This slide highlights a range of emerging strategies and innovative therapies that could revolutionize type 1 diabetes treatments. This slide outlines major milestones and discoveries in T1D research and treatment advancements over 100 years. Maybe 50 years, yeah. You can see here the latest things, 2023, first FDA approved cell-based therapy for type 1 diabetes. And also 2024, as you can see here, Cernova cell pouch success, and it's a kind of a company, and stem cell reverse diabetes. The thing that I talked about it before, a woman reversed type 1 diabetes after receiving a transplantation of insulin producing cells. I mean the chemically induced pluripotent stem cells. This slide explains the function and benefits of the insufflone and iPort, which are devices used to simplify insulin delivery. Insufflone is a small catheter inserted into the fat layer under the skin, staying in place for up to 4 days. It is secured with an adhesive sticker. A needle is required to insert the catheter, but after that, insulin can be injected pain-free through the silicone membrane without piercing the skin each time, which is promising. iPort is the other option, works similarly to the insufflone, but uses a needle-based inserter to place the cannula under the skin. Insulin can then be injected through the cannula with a regular syringe, also eliminating the need to puncture the skin multiple times. Maybe a diabetic patient have to inject 2 or 3 times a day. So both devices offer a more convenient and less painful alternative to daily injections through the skin, improving the quality of life for individuals requiring regular insulin administration. This is the other device. This slide discusses the self-orienting millimeter actuator, or SOMA, tortoise-inspired pill-sized device for drug delivery, specifically for insulin. The key features: SOMA is about the size of a pea, modeled after the self-writing shape of a leopard tortoise. It contains an insulin tip and is made from low-density biodegradable polyester sugar actuators and stainless steel spring. How it works, how the SOMA works. The SOMA is swallowed like a regular pill. It localized to the stomach lining due to its low center of mass and tortoise-like shape. It self-orients and attaches its injection mechanism to the tissue wall. and gastrointestinal fluid dissolve the sugar actuator, releasing the spring. This action drives the insulin tip into the stomach tissue, and the insulin dissolves into the tissue, delivering the medication. It's very, it could be very useful to the patients which have the kind of problems with injecting daily insulin. Yeah, this slide describes two critical technologies in diabetes treatment: PEG 01 cells. There are proprietary pancreatic endoderm cells derived from an inexhaustible human embryonic stem cell line. Directed differentiation allows these cells to produce insulin and other therapeutic hormones like amylin and glucagon. This device name is Encaptura delivery system. This is the proprietary encapsulation mediated device that is both immune protecting and retrievable. The Encaptura system acts as a kind of semi-permeable barrier, allowing essential nutrients like, I don't know, glucose, oxygen, proteins, vitamins to enter, while protecting the encapsulated cells from immune cell attacks. The device provides therapeutic output like insulin, amylin, and glucagon, while maintaining the integrity of the encapsulated cells. Yeah, this is the technology cell. And this slide shows the PEG 01 PEG direct vasculogenesis. Okay. This company, Vertex, just purchased that company and now working on different strategies. You can see here there are two different cell lines. VX880. This is a kind of an investigational allogeneic stem cell drive, fully differentiated insulin-producing islet cell therapy, and manufactured using proprietary technology. It's being evaluated for patients who have type 1 diabetes with impaired hypoglycemic awareness and severe hypoglycemia. VX880 is being investigated as an infusion into the hepatic portal vein and requires immunosuppressive therapy to protect the islet cells from immune rejection. Recently, they published two different papers, one 2023 and the other one 2024. VX264 is an investigation approach encapsulating cells in a protective device to be surgically implanted in the body. VX264 or 264 is being evaluated without the use of immunosuppressive therapy, as the devices are designed to shield the cells from the body immune system. Okay. This slide discusses the Treg therapy, specifically focusing on the role of Sonoma Biotherapeutics. There are different companies in the world working mainly established in the United States of America. Sonoma Biotherapeutics, which is located here in the Bay Area, is developing therapeutic regulatory T cells to restore tissue homeostasis and reduce inflammation. In conditions such as autoimmune disease, activated effector T cells or T effector cells cause tissue destruction, like type 1 diabetes, we can see here. Antigen-presenting cells promote epitope spreading and effector differentiation in the lymph node, further exacerbating the immune response and inflammation. Treg restoration of tissue homeostasis. Therapeutic Treg cells are engineered. In this company, they engineered the T cells, regulatory T cells, to suppress excessive immune responses by inactivating APSCs and depriving effector cells of IL-2, reducing their ability to proliferate. The result is reduced inflammation and tissue repair, leading to the restoration of tissue homeostasis. This slide introduces the hypoimmune or HIP editing technology, focusing on Sonoma Biotechnology. This is another company which is located nearby here in the Bay Area. near San Francisco. This approach for soda islet transplantation in diabetic therapy, the key elements include hip editing. I talked about it before, hypoimmune islets. The process involves editing cells from rhesus monkey donors, specifically B2M and C2TA cells, and depleting MHC class 1 and 2 cells while maintaining CD47 positive expression. These edited cells are transplanted into diabetic monkeys, which serve as recipients. And they induce diabetes, and they use these hip editing technology to transplantation and controlling the diabetes in these primates. Diapcel is a breakthrough cell therapy aimed to transforming the treatment landscape for patients with type 1 diabetes. Key points include this company, they derive from pigs. Diapcel consists of insulin-producing islet cells that self-regulate and secrete insulin within the patient's body. Actually, I searched about this company. I couldn't find anything, any update. I don't know, maybe they don't work currently on diabetes, or something happened or collapsed. But this is a very breakthrough company. They use the islets from pigs, which is very promising. Many companies are developing innovative therapies for type 1 diabetes, from regenerative medicine to immunomodulation. For example, here, companies like Ysight and Vertex Pharmaceuticals are the forefront of developing stem cell-derived beta cells, while Prevention Bio focuses on immune therapies like teplizumab. This slide highlights different companies focused on advancing stem cell therapies for diabetes, particularly type 1 diabetes. You can see here lots of the companies which are the pioneers in type 1 diabetes treatments. There are vast majority of pipelines here. At the forefront of type 1 diabetes research, clinical trials are currently investigating cell-based therapies, beta cell regeneration, and immune tolerance approaches. As the October 2024, over 376 clinical trials are registered on clinicaltrials.gov, showing the rapid pace of innovation in the field. Actually, I searched for cell therapy of diabetes, and 376 clinical trials and clinicaltrials.gov is present. Okay. In this slide, I'm going to just summarize the FDA-approved products and medications for type 1 diabetes. I'm just going to conclude all things. Recent FDA approvals, such as the Medtronic MiniMed 780G, insulin delivery system, Dexcom G7 CGM. As you can see here, Dexcom G7 continuous glucose monitor. And for immunotherapy of type 1 diabetes, you can see here teplizumab, FDA approved to delay the onset of type 1 diabetes in at-risk individuals. Lantidra allogenic islet cells for transplantation is the first FDA approved allogenic islet cell therapy for type 1 diabetes. It is indicated for patients who have unstable type 1 diabetes and experience severe hypoglycemia, and awareness. These are this slide represent the under development or clinical trials for type 1 diabetes. Beta cell replacement and regenerative medicine, I talked about it. Vertex Pharmaceuticals VX880 in clinical trials, not yet FDA approved. SGLT inhibitors for type 1 diabetes, and also artificial pancreas system, beta cell encapsulation device, emerging gene therapy approaches, CRISPR, I don't know, like CRISPR-Cas9. It's not FDA approved, but yeah. And islet cell transplantation, stem cell derived islet therapies are in clinical trial, but not yet FDA approved. This is the kind of the timeline of key milestones in diabetes research and technological innovation over the past century. You can see here any technology innovation and milestones. And this is the schematic of a kind of overview of diverse therapeutic strategies being developed for type 1 diabetes. I don't know, you can see here that the cause of type 1 diabetes, insulin insufficiency, and different treatments for type 1 diabetes and possible treatments for this disease. And final thoughts. In conclusion, integrative approaches combining advanced insulin delivery system, immunotherapies, and cell-based treatments are revolutionizing type 1 diabetes care with FDA-approved, therapies like teplizumab and lantidra, as well as emerging technologies like gene editing and stem cell-derived islets. The future holds great promise for both improving patient outcomes and moving closer to a cure. As a landscape of diabetes care continues to evolve, the integration of personalized therapies, next-generation cell-based treatments, and advanced insulin technologies will transform how we can treat type 1 diabetes. The goal remains clear. The goal remains clear to not only manage the disease, but to potentially cure it. Thank you. I would like to extend my heartfelt thanks to the audience for their time and attention throughout this presentation. A special thanks as well to Parvaz School for organizing this wonderful opportunity. Your support and interest are truly appreciated. I'm also available to answer any questions you may have. Please feel free to ask, and I'll be happy to provide further explanations and also clarifications. Thank you. If you have any questions, I'm here to answer all questions. Feel free to ask. Of course. Of course, yeah. Thank you. If you don't have any question, Yeah, we can terminate the meeting and presentation session. Okay. Have a good night.
Well, just
Thank you.
wanted to say thank you for your great talk. It was really informative and inspiring.
Thank you. Do you have any questions?
No, it was completely great, and I was wondering that how you could speak much well, and I really used this session.
Thank you.
It was
Thank you.
really
Appreciate it.
useful for me. Thank you.
Of course. Yep. Please. One of guys, I think, raised hand. Which one? Yeah, I talked about this woman. It was a kind of the treatment for a woman, and which published recently, 2 weeks ago, maybe. Yeah, and I think I have the slides, the presentation about her. Uh, a minute. Yeah, this one. Yeah, this one, this patient. They published in, I think it wasn't 2 weeks ago, and they just let me. Yeah, they transplanted the chemically induced pluripotent stem cells, stem cell derived islets under abdominal anterior rectus sheet in this type 1 diabetes patient. This study showed promising results, leading to the restoration of insulin secretion and improved glycemic control. 1 year follow-up. Actually, it's ongoing. It's the first year of follow-up. Maybe next year or the years later, they can have additional comments or kind of complementary results for this study. And it's just for just one patient. Maybe they should continue with several patients, and if this promising strategy works well, it would be really great full cell therapy option in the future for type 1 diabetes. Yeah, actually, I should announce the other strategy. A company called Cernova. They announced the positive interim data from phase 1 to clinical trials, demonstrating the long-term survival and functionality of transplanted islets in their cell pouch system. It was a kind of pouch for type 1 diabetes. This study showed that more than 5 years post-transplantation, the islets remain healthy and well vascularized in this pouch, producing insulin, glucagon, and somatostatin without any fibrotic tissue formation. But these are ongoing procedures, ongoing studies, and they need to be more deeply work on these kind of treatments. Yeah. Of course. Okay. You asked the question, what's its benefits? Actually, we are looking forward to have a kind of a good option on the table to treatments. The most important thing that highlights for this study, the patient received autologous chemical induced pluripotent stem cells, which is one of the most important things that we should consider. And they just got the cells from this patient and use some chemical reagents, I don't know, like small molecules to reprogram the cells, and then produce the stem cell-derived islets from the same patient. The second option is the insulin independency in this patient, which is one of the main goals for type 1 diabetes treatments. So, and also hemoglobin A1C levels are decreased in this patient. These are the most important benefits, and actually it's not the a long-term follow-up. It was just for 1 year. It's too early to say that's a kind of effective cure and kind of treatments for type 1 diabetes, but efforts are still ongoing, and we're waiting to have a kind of very strong and comprehensive method to therapy of type 1 diabetes and other types of autoimmune disorders. Yeah, the most important things and the findings for these two kind of strategies are just insulin independency after a while. Yeah. Sure. Okay, thank you. Thank you very much for your invitation. It was a great honor to be here with you guys. Thank you, Dr. Jalili, and also his great team at Parvaz School. Yeah, thank you. That gave me this opportunity to be here and talk about future integrative directions and type 1 diabetes treatment. Maybe in the future we can have other sets of presentation. Thank you very much. Thank you. You're the professional. Bye. Have a good one.